Hello and welcome to the components episode of my Physics in Bevy, focusing on all the components from Bevy Rapier. The concept of this video is going to be an overview of every single component that Bevy Rapier provides. This isn't going to be an instructional video of how to use or get these components. For some things, like joints, have constructors that will then insert the correct components onto all the corresponding entities, or things like the player controller that have a lot of configuration. But if you, like I recommend highly, use the Bevy editor please, you will notice some of these components in the side panel, and it's good to know that they exist and what they actually represent. And this also plays on the concept that I mentioned in my previous video, that knowing that these things exist is half the challenge of actually being able to research this kind of thing, because you know what to search for. The Bevy Rapier webpage is incredibly useful, but you need to know that the feature exists in order to go looking for it. I'd like to do a thank you to Manuel for sponsoring this YouTube series on my Patreon. If you'd like to help support the channel, you can find a link to my Patreon in the description down below. So to find all the components inside the Bevy Rapier project, I've just done a simple regular expression searching for anything that derives the component trait. If you've been using Bevy long enough, you know that any struct can be a component, but they have to derive the component trait so that it can basically self-document that these components exist, making it really easy for third parties of your crate to quickly find what components you have available. I'll leave a copy of the regular expression in the description so that you can use it yourself, either on the Rapier crate or on other crates that you would like to explore what components are available. This also works for resources and events, since they also need a derive to function. One thing you'll notice when going through components is things like vect, rot, and real. These represent types that may change depending on if you're using a 2D or a 3D implementation of Bevy Rapier. The vect represents the vector type and will change between a vect3 and a vect2 based on Bevy Rapier 3D or 2D respectively. The rot is the same. Rot will represent the rotation, either as an F32 in 2D or a quaternion in 3D. And finally, real. Real refers to the precision of the crate and can be either F64 or F32. First, we'll start with the character controllers. These are the most intense of the components, but also the least required to learn, because they are basically just the components to interact with the pre-provided player controller that Bevy Rapier provides. The first component is the kinematic character controller, and this is all the interactions that you can do and settings that you need to configure for the player controller, such as things like auto step and whether they snap to the ground. Moving on, we have the kinematic character controller output. This is one of those components that you need to know it exists in order to get the maximum potential out of Bevy Rapier's character controller. It has information that you may want to query about what happened to the kinematic player controller. Things like, is the controller on the ground? The desired translation that you wanted the controller to have, the effective translation that the controller actually moved, and the collisions that the controller had while moving. That's enough for the character controller. Next, we'll move on to joints. Bevy Rapier provides two types of joints: impulse joints and multi-body joints. Impulse joints being joints that actually use the physics system to simulate how they move, but can be a bit jittery, and multi-body joints that are a tree structure and apply the correct translation onto each subsequent point in the joint. This is more computationally expensive, but has more stable results and won't result in the same jitter, but can have more rigid looking animations. Bevy Rapier stores the information about the actual joints themselves inside the physics world, so you can access using the Bevy Rapier handles that are provided by components attached to the entity. The Bevy Rapier website is a great source of information, and it will actually tell you all the different types of joints that you can use in 2D and 3D and how they are able to move, such as in 2D. There are significantly less types of joints than in 3D, since 3D can also move along the 2D plane specifically. The components related to joints themselves are not that complicated. You have the impulse joint, which just tells you the parent and some generic joint information, and the multi-body joint, which is the same, just telling you the parent and the generic joint information. The rest of the data about joints will need to be fetched from the physics world using the joint handles. Next, we have the rigid body. It works very similar to joints, that a copy of information is stored inside the physics world, so you end up with a rigid body handle, which allows you to access the object inside the physics world that this rigid body is representing. Next, you have the rigid body itself. This is just an enum that describes what type of rigid body, and therefore what information gets copied across into the physics world, and what information is forcibly set back from the physics world. Next, we have the velocity. This is another situation where you'll see different types depending on which physics version you are using, 3D versus 2D. where the angular velocity is an F32 in 2D and a vect3 in 3D. Next, you have the additional mass properties. This allows you to attach additional mass to a rigid body. This can be done directly by specifying an additional mass in either the rigid body or any of its children, or you can specify in more detail information about the mass, such as its center of mass and offset when it comes to impulse and inertia. The mass properties also have a read mass properties variant, which allows you to access the mass's properties, such as its offset of center of mass and inertia, from the physics world. In my previous video, I talked about how sometimes you need to add specific components in order to be able to read data back out of the physics world. This is one of those cases. Next, we have the locked axes, which is a U8 representing the potential states that a component can be in. There is lock X, lock Y, lock Z, which can both be applied in translation and rotation to prevent the rigid body from being able to be moved in these particular directions. There is also a locked variant for both translation and rotation, which will apply all three of the corresponding flags. There's also an all variant, which will lock all possible movement on an A entity. So why you would want to use this, I do not know. Next, we have external force. This allows you to apply a constant external force onto a rigid body. This is something like wind, which would be a constant force applied to the player, pushing them in a specific direction. Though there is also an external impulse component, which will apply an instantaneous effect rather than a constant effect. This can be used to things like boost pads, where you don't actually want the force to be applied while the player is standing in a specific place, but instead just to be applied instantaneously, launching the player in the air. You could also use this in a physics-based platformer to do things like jumping. Rather than you directly manipulating the velocity of the character, you instead apply an external impulse, which will force the player up as if they jumped. This would allow for things like jump height to automatically be affected by the character's mass, since you're applying a force and not just setting their velocity in an upward direction. Next is gravity scale. Gravity scale is simply a modifier at which the gravity is multiplied by when affecting this particular rigid body. This allows you to do things like have certain objects not be affected by gravity. Other objects, such as feathers, would fall more slowly by setting their scale lower, and things like steel balls could fall faster by setting their gravity scale higher. Gravity scale is not to be confused with restitution, which would be the representation of air resistance in the world. So setting the restitution different for feathers and balls would mean that they all fall differently by air resistance slowing them down, rather than an actual effect on the gravity, whereas gravity scaling will actually make the object appear lighter. This could be seen using a feather as an example. Setting its gravity scale low will mean that it will fall slowly, but if an impulse is applied to fire it up, it will fly up really quickly. Whereas setting a higher restitution will mean that it will fall more slowly, and if it gets pushed up, it will slow down more quickly. Next up is the CCD component. This is short for Continuous Collision Detection, and has just a bool to enable or disable this. I don't know why they've abbreviated the name to CCD, but those of you who aren't aware, Continuous Collision Detection is a method that allows for objects to collide, even if they're moving too fast that they would actually have missed the collision in a single object. I believe this is usually done by extruding the size of the collider along the axes so that it is possible to detect collisions that would not have happened on fast-moving small objects. There are usually restrictions on what type of colliders can have continuous collision detection, since they need to be able to extrude in the direction of the collision. If I remember correctly, this is usually done by using a sphere and extruding a second sphere along the entire length that that object moved, and treating that as a capsule collider to check to see if anything would have collided from where the object left and where the object ended. But you cannot arbitrarily extrude things like squares. Instead, continuous collision technique on things like squares will place a sphere on each of the corners and extrude them out like it would for a sphere, and then see if any of those collide in order to determine if the cube would have collided with anything. I don't know the internals of Bevy Rapier, but I will hopefully have a graphic on screen demonstrating what I mean. Next up is dominance. This is, again, another component that if you didn't know it existed and hadn't programmed your own physics engine, wouldn't know to look for, but it's incredibly useful. Basically, every object is given a group from -127 to +127. And if these groups are identical, physics will happen as normal. But if one of these objects happens to have a higher group than another, then all physics interactions will treat the higher group as having infinite mass. This is what allows for games to do things like have the player not be able to be pushed around by objects in the physics world, since the player can be in a higher dominance group than all the objects in the world. This means that the player can push around all the balls or the objects in the world, and the objects will be pushed around but will not push the player around. This would be very useful in puzzles and things like that, where you don't want the player's movement to change based on the objects colliding with the player. This could also be done by representing other things, such as really big blocks in the world having a higher dominance group than other dynamic objects that may bounce around, and then the player may have the same or a higher dominance group than those objects, allowing the player to push the blocks, but other objects not be able to push the blocks around. Next up, the sleeping component. This component indicates whether an object should go to sleep and if it is currently sleeping. When an object is asleep in a physics engine, things like its position and velocity are not recalculated each frame. This allows for the physics engine to be much faster, since it can put all the objects to sleep and then it only needs to do basic bounce checks to make sure that nothing collided with the object and may have woken it up. Up next is dampening. Dampening is basically the air resistance of an object. It will constantly draw the object back towards zero. Linear dampening being the actual movement, and angular dampening will be rotational movement. Then we have the translation interpolation. This allows for entities with rigid bodies to have their position automatically interpolated between two rigid body positions set by the physics engine. I'm not exactly sure what this means, but I think it means that the object won't immediately snap to where the physics engine placed it, but instead allow it to slowly move from one position to another. This will allow for a physics engine to run at, say, 30 FPS, but your game to run at 60 FPS, and the objects will interpolate between the physics steps. And then we have rigid body disabled. This is very similar to sleeping, where the rigid body will be turned off and no longer have its physics interactions calculated. Except this is explicitly set by the user and will not be undone by the physics engine until the user explicitly removes the component. That's all for the rigid body specific components. Next, we'll move on to collider related components. Very similar to rigid bodies, collider information is also stored in the physics world. So Bevy Rapier provides a collider handle as a component on specific entities that have colliders. First up, we have async colliders. This is a temporary value that represents a collider based on a mesh that may or may not have loaded yet, and will be removed once the mesh has been verified to be loaded, and therefore the mesh collider can be used instead. Next is the async scene collider. This is the same as the async collider, but represents objects in the child of a scene that may or may not have loaded completely yet and will be replaced once the scene has completely loaded. Next up is the collider itself, which basically contains the information about the collider that is on the rigid body. Though, because it is possible that you may want multiple different shapes and to combine shapes in order to make the collider for your object, colliders on the children of entities with rigid bodies will also be applied as if they were on that rigid body entity itself. So to chain multiple colliders, you put them on the children. Next up, we have the collider scale. This can be either relative or absolute, and will scale the collider accordingly. On relative, it will use the global transforms in order to determine what the relative size of that collider is based on all of its parents. Whereas if absolute is set, then the collider is simply only scaled by an absolute value and will not be affected by the size of its parents. Next is the sensor component. The sensor component is a zero width marker flag that indicates whether a collider actually represents something you can collide with, or just a sensor that will trigger collisions for other functions to interact with. If you have, say, a door that opens when you walk up to it, you would use a sensor, since you don't want the player to be able to collide with the indicator that the door is going to open. Next, we have the collider mass properties. This is the counterpart to the mass properties on a rigid body. You can specify the same information that you would have for a rigid body, but with the additional fact that you can specify a density, and this will automatically work out what the mass is based on the size and scale of the collider and its shape. Next up is friction. Friction indicates how much energy is lost when two colliders are moving against each other. A high coefficient of friction will result in objects slowing down really quickly when they come in contact, whereas a low coefficient of friction will result in objects slowing down much slower. Coefficient of friction of 0 will mean that the object will slide indefinitely when in contact, since no energy is lost. This is similar to how things like Minecraft and ice work, where the ice will cause the player to slow down less. Though it does specify that the coefficient of friction should always be greater than or equal to 0. This is because if you set a coefficient of friction less than 0, it will actually result in an object accelerating when in contact with the object, rather than decelerating, which can lead to some issues. There is also a combination rule. The combination rule allows you to specify whether the values are averaged, whether the smallest value is taken, the largest value is taken, or whether the two values are multiplied together in order to get a new coefficient of friction. Next up is restitution. Restitution represents how much energy is preserved when two colliders interact. This value should always be greater than or equal to 0, because a value less than 0 indicates that if two colliders collide, they should actually start continuing in the same direction with greater force. This can be seen as why antimatter annihilates with matter, in that if the two objects combine, instead of pushing each other away from each other like normal matter would, they would actually increase the force at which they were pushing into each other into infinity. If you set a restitution greater than 1, this indicates that the collision actually gains energy when they collide, rather than losing it. This can be done, you can see an example of this in my Pong game, where I set the coefficient to greater than 1 in order to have the balls bounce off and get faster and faster every time they hit the paddles. Restitution also has the same combination rules as friction. Up next is the active collision type. This is a marker indicating what types of collision the particular collider is allowed to interact with, based on what type of rigid body is it attached to, and what type of rigid body the collider it is interacting with is also attached to. This is things like dynamic colliding with dynamic colliding with kinematic, dynamic colliding with static, kinematic colliding with kinematic, and so on and so on. I'm not quite sure how you could have a static colliding with a static. I guess this could be used for terrain checks, such as when you spawn in a map and you can then check to see if there are any objects in the map interacting with any other object in the map that cannot move. Up next is the group component. Group represents what collider group it belongs to, and there are 32 collider groups, represented by one bit in the group U32 struct. Two colliders from the same group are able to interact and collide, whereas colliders that do not share at least one group in common will not be able to collide. This would allow for things like physics in games where friendly fire is not an option, since you could specify that objects fired by the enemy are in your collision group and objects fired by you are in the enemy's collision group, which means that your projectiles can no longer collide with your friendly colliders, but will collide with enemy colliders. There are also a whole bunch of other situations where these groups are useful, though it is important to note that there is actually a separate component used when you want objects to skip interaction but still calculate collision. When they're in separate groups, collision is completely ignored and no calculation is performed, so you cannot extract any information about collisions between objects in different groups. Up next is collision groups. These are an even more restrictive version of groups, which allows you to specify not only your membership in a specific group, but also what groups are actually allowed to interact with you, and these two groups do not have to line up. This allows for situations where you ignore all collisions, except for situations where you are a member of their filter and they are a member of your filter. I personally don't know where you would use this over using straight groups, but I guess there are situations where you want certain types of projectiles to have friendly fire, but other types not, so you could set it up in such a way that certain projectiles have friendly fire as part of their filter. Next are solver groups. Solver groups are less restrictive than collider groups, in that they will actually calculate collisions. They just will not apply any physical force. This means that objects from two different solver groups will pass straight through each other, but they will still trigger collisions for the sake of collision checks. They just will not bounce off each other or have any other interaction on each other's forces. They will simply indicate where and how they collided. Up next is active hooks. This allows you to modify specific parts of how the physics interaction works. You can do things like filter contact pairs, filter intersection pairs, and modify solver contact. I personally don't know enough about the physics engine to know what these hooks actually do, but by using this component you can enable or disable them respectively inside the physics engine and have whatever interaction they represent applied or not applied. Next is the active events flag. This struct indicates what events should be emitted by this specific collider. In the previous episode, I talked about that there are collision events which tell you the collision between two colliders and whether it's just started or just finished, and the force event colliders, which tell you more details about the specific collision event. Active events will allow you to specify whether a collider gets to emit those particular information, allowing you to optimize your game by cutting down on things like objects in the world where you do not care about any interactions, force from them, whereas the player may be important to collect the force information from. Next is the component contact force event threshold. This is a F32 that represents how much force needs to be applied before a contact force event is emitted. Next is the colliding entities. This is another one of those great components that knowing it exists is really useful, since whenever I've wanted to do collision detection, up until making this video, I would have always grabbed the Rapier context and queried for any collisions with the entity that I am requesting. By attaching the colliding entities component onto the entity that I care about, this will allow for the Rapier engine to extract all the collisions and insert them into this hash set. When it finishes the physics step, I can then just query for the colliding entities struct in order to look up all the entities that collided with that specific entity, without needing to access the Rapier physics world context. And finally, we also have a collider disabled. This is the same as the RigidBody disabled, allowing you to deactivate a collider as the programmer and then have its interactions not calculated until you remove this component, re-enabling the collider. Next, if you have the debugging feature enabled and the plugin added to your game, it is possible to add the collider debug color to a entity with a collider, and that will specify what color you want that specific collider to appear when rendered for debugging. This can be useful for doing specific types of colliders, maybe in different groups, having different colors, so that they can easily be recognized when you are doing collisions. Please don't forget to subscribe and like the video so you don't miss out on future content on Bevy Rapier or other content that I post on my channel about Bevy. Thank you for making it this far in the video. The next video in this series will hopefully be how to include Bevy Rapier into your actual application and how to set up an object in order to have physics interaction with it.